I'm Lizzi. I've spent the last 4 years of my job writing in a functional language called Clojure. When I tell people I write Clojure and they look at it, some people react in ways that make me kind of sad. They say that's too weird for me or I'm not smart enough for that. That is not true. Functional programming has been seen as kind of arcane, but it seems to become a little more popular thanks to some languages making it easier for the average developer to adopt. If you were here back in November, you would have seen Kyle Shevlin talk about how to use functional programming in JavaScript. I adore functional programming. It has saved me so many headaches that I've had working in other paradigms, and I want to convince you that it's worth it for you to try. Alright, so functional programming is a paradigm. This means it's a style of designing and structuring code. Object-oriented programming, which you might be familiar with if you haven't done functional, is a paradigm which has to think about and write your program in terms of the objects that it handles, and to encapsulate the interface for handling those objects along with the data in the object itself. The functional paradigm, like most paradigms, ends up being a spectrum of certain features, and I say spectrum because while there are qualities that you want to strive for as a functional language, whether a given language implements them and how strictly they do it can vary. This is why I encourage people to use a language designed just for functional programming when learning it, but it'll help you develop better habits. The one feature that ties all functional languages together, though, is functions. So objects versus functions can look like this. If you have an application that stores and manipulates data about a human, an object-oriented language, like the Python example on the left, would define a human object and be able to set and change attributes about the human. The example on the right is Clojure. Clojure doesn't have objects. We instead represent objects as data, in this case I'm using a map up top being hello. I just assign a map with age set to 42, and that's just data about a person. Next I define a function using that defn called updateAge, which will then associate a new age to the age key in the map. We call the function, and the changed data is output. That Clojure code might have looked really strange to you. This sometimes stops people from trying it, but it's the language that I recommend most people experiment with if they want to learn the principles of functional programming. Even though it looks weird, it has a straightforward syntax, and it's not very strict. It's worth getting used to because it's really friendly once you do. So why the heck does putting functions first matter? On the surface, it doesn't yet. It's just another way of looking at the world. But it turns out that this way of designing programs, along with a few other properties, gets us some benefits that are hard to get in the object-oriented world. And this is where it gets fun. So let's talk about what we want from our programs, ideally. We want them to be testable without much complexity or setup. We want them to be predictable and easy to reason about. We want to avoid surprises like race conditions. And more, we need them to be concurrent, which adds another layer of complexity to how your program works and makes it harder for humans to reason about it. So let's get into how functional programming can help with that. I'm going to show you some examples that might seem trivial or obvious when they're in small chunks of code, but they become exacerbated when we're talking about a larger code base. So here's some Ruby pseudocode. We have a game store class. It has an ID and data about the home and away teams, their name and their score. So say our application is backed by a database. Some other system out there is pushing score information about games into the database, and our application can fetch the data from there. So we want a method, is my team winning, where people can get the most recent information about the game and find out if their team is winning. To get the most recent information, we fetch the data from the database. Then we do some updating of game source data to check if our team is winning. You can imagine the code that does that. I couldn't fit it, sorry. The is my team winning method returns true or false. You might already be spotting some flaws with this code. How can we unit test this method? If you're not familiar with the term, it means testing small pieces of your code like a method in isolation, but this method calls a database. If we try to write a unit test, like this RSpec test, it becomes clear that we can't test it without setting up a database. There is no way to give any input without it, and we can't assert what the result will be because there's no information about the database. And when you run it, your code attempts to contact the database and errors. So an extremely common way to deal with this problem is to fake the database, also called mocking or stubbing, in order to unit test it. We replace the query database function with a stub that returns a fixed set of scores there, 2 and 0, so that we have concrete data to write our expectations against in our test. And now we can finally assert that our object can properly compare scores and give us the answer we want. I should note that this is a bit unfair of an example. There are ways to avoid this problem in Ruby code. But this is also a bad habit I see really frequently in Ruby code, And I think that learning functional programming can help with that bad habit. And in more complex code, functional programming principles make this frog pulling easier to avoid. So how do we do this with functional programming? The most important thing we need to do here is maximize the amount of pure functions in our code. So a function is pure when the only thing the value of the output depends on is what input you give it. So for example, we define a function that multiplies an input, or an argument, by 2. If you give it 12, you'll get 24. And that's the same is true for any number you pass as an argument, you'll only get one output. In contrast, this is not a pure function because it tries to multiply the input by a random value. And that random value isn't an input to the function. It's not an argument. So you can't predict the output from the input. It's not deterministic, it's not pure. Using any values that can change or come from a source outside your program's scope that you're handling right now is called side effects. In functional programming, we delay performing the side effects until the last possible minute. Side effects are the sorts of things that we have to mock because either our program isn't responsible for them or their values can change and affect the output. And so the results that we get from tests are changing all the time. This is usually what's going on when you inflate tests. Let's look at how a functional program would do this. So first, you define what your internal data structure will look like. It's always a good idea to do this, no matter what language you're writing in. It helps clarify what you're trying to do. So this is an example of what the data will look like in Clojure. It's a map with keys on the left and values on the right. There's no commas or brackets or anything. If you're writing in Haskell or Scala, you might define a type, but in Clojure there's no types, so we just document what we expect. That's sometimes a problem. Next, we write pure functions that do just the data manipulation you need inside the program, using only that internal type. In this case, the business logic of our program is about taking game data and deciding whether my team is winning. So we define a function to take game data and the name of your chosen team as arguments. And this is the function that knows how to answer our main question, but how to get the data is outside of its concern. It just does the logic. And we can see it returns a Boolean. Since it's doing logic-based only on the inputs of the function, it's pure. We can unit test this. Happily, if you couldn't do whatever the example. The next step is to write methods that change your internal data representation to your external one or back and forth. Our database returns scores in a different format than we want to use internally on the right there. It doesn't store team names. So we need to be able to update it to our internal format before we can pass it on to the is my team winning function. We can write a pure function that translates the database's format into our internal representation. Again, we're not creating the database yet. We're just passing you data that we already have. This allows the function to still be pure and unit testable. And now we write our side effecting function. We want to do as little work as possible within isolated functions that do side effects. This, all it does is go fetch the record from the database and return it. Since it contacts the database, we can't unit test it, but because it's simple, we can write a simple acceptance test for it. And this is our top layer, which you can think of the API consumers are supposed to interact with. There's a lot going on here, but the main important part is that this composes all the functions that we've created together in this sort of passing data. And since all of our components have been unit tested thoroughly, you just need a simple smoke test for this. 2/3 of this function has already been unit tested. Avoiding side effects for as long as possible also reduces complexity, because for your pure functions, you only have to reason about what it will do within its own scope. You don't have to worry about what anything else will do. The more building blocks you have that are simple, the easier it is to build something bigger. Another really important property of good functional programming is immutability. You might be familiar with this from other languages. Many languages have mutable and immutable data types. If you don't already know, immutability is when you can have a reference to a value, call a function to transform that value, and your original reference points to the transformed value. In our first example on the left written in Python, I create a list, then assign that value to 2 different variables, first list and second list. And then I try to change second list. When I print them both, you can see that they're both changed. Those things point to the same list. In my second example, when I assign second list, I call list on the value of first list, which creates a copy. Then when I change second list, only second list has changed. It's because they're pointing to two actually different data structures, but one has been changed. This is not true immutability. Lists are still mutable in Python, but this is how you would implement a mutable data type. If you like visual representations, this is a good one. If We start off with just a blue box up at the top. You have a blue box that you call make a green on in the next frame. And then in the last frame, you actually have a green copy. If you want to be able to refer to the green box, you have to assign it a label. This is helpful for a number of reasons, although it's not obvious on the top. Just like, why are you creating extra work for yourself? I want to be able to change the things that I'm doing and need to handle it. But all of the reasons this is helpful is because it helps us avoid surprises. Immutability forces you to design your programs in a way that really helps whenever multiple parts of your program want to use the same data. When you have issues sharing state or with race conditions, it's usually because one part of your program updated a value and another part of your program wasn't prepared for that. Here, that's impossible. References will not change their values unless you explicitly choose for that to happen, and then that's criminal. It can be difficult to get used to writing programs this way at first. But after reading a couple of examples, it gives us a light to write async or concurrent programs in functional programming. Because our pure functions with immutable data include guarantees most languages don't. For example, when you have concurrency logic in a program with immutable data, you have to include locks to make sure that multiple things don't try to update or read your data at once. You have to do that a lot less often in functional programming because you stream the data in such a way they're not interfering with each other. In fact, Clojure is one of the best interfaces for writing reasonable concurrent programs. Erlang, another functional language, is also famous for this. Mutability in general just makes your program more predictable. This is all about mitigating the confusion that complex state brings into a program. You try to reduce the effect state has on a program. If your program's core is pure functions, you can always show that they will produce the same output for a given set of arguments, then you can show the same thing when you compose them. And this one is hard to improve. So just let me offer a testimonial. I want to write functional languages forever. I find I'm able to express my ideas and create function codes so much more quickly than before. I write every side project I can get away with in Clojure because I just don't have to run into as many problems. And I don't trust it when people say code is elegant or terse. That's not what I'm saying. Sometimes that means harder to understand for people who aren't you, but that's not the case here. I don't have headaches trying to figure out what weird behind-the-scenes state changes are happening as code somebody else wrote most of the time. Clojure's lack of typing does hurt here in whatever code base. So there are many things that we could talk about, and I wanted to, but I don't have the time. So you'll have to discover them for yourself, because learning functional programming can make you and your code better, and it's worth the time to learn. And to learn it, these are all the things that you can try. The good books on Clojure to try are Clojure for the Brave and True if you want a fun one, and The Joy of Clojure if you want a serious one. There's online exercises on Clojure and exercism.io for just trying it out. This is the way I like to do it, just try different little data structure puzzles. If you write front-end code, you can write in Clojure script, which is the same as Clojure, but it compiles to JavaScript, or Elm. If you want all the benefits that functional programming can give you, like types and correctness proving, you can also try Haskell and Interest, they've just got a higher learning curve. Those are next on my personal list. And if you want to talk about functional programming or ask questions, you can tweet at me at cosmic_peril, and there's also a monthly Clojure PDX meetup that is hosted at my office. And this was my favorite slide, and it's not late.